So my name is Mario, and I'll talk to you today about some of the low latency network interface work we've been doing. So we're part of a RAMCloud project at Stanford. And for those who are not familiar, RAMCloud is a durable in-memory object store system. And it's meant to run in a data center environment on tens of thousands of machines. But even that's where it's intended to run, its goal is still ultra-low latency. So the goal is to achieve 5 microseconds for an application round-trip latency. And to achieve that goal, it's necessary for the application code itself to run very fast. So the application code runs in under 1 microsecond. And so when we have this application that runs this fast, it's only natural to look at other sources of latency for data center RPC to achieve our 5 microsecond overall goal. And so we've done this, and we've noticed that network interfaces actually can have pretty high latency. Depending on which network card you buy and, importantly, how you configure it, you can easily get into tens of microseconds of latency. And then we notice that power management is also important. Unless you disable it, you can end up incurring up to 100 microsecond latency penalty. Now, thankfully, data center network switches are pretty fast. You can get under a microsecond over several switches. And our cable length is not that high inside a data center. So those two are not an issue. But the network interface and power management are. And this is what I'm going to talk to you about today. I'm mostly going to cover the network interface and touch a little bit on power management. All right, so let's get right into it. There we go. I'm going to walk you through a packet transmit and a packet receive on a typical commodity Intel 10 gigabit network card. So when a transmit machine wants to send out a packet, the first thing it does is it prepares a descriptor in host memory. This descriptor will typically only contain a packet pointer and length. And once it's prepared in host memory, it has to get transmitted over to the network card. And so this is typically done by the CPU writing to a doorbell register in the NIC. And then the NIC will use its DMA engine to fetch the descriptor out of main memory. Now, once it has a descriptor, it knows where the packet is in main memory. So it can go ahead and do a DMA read to access the packet itself. Once it has the packet, it's ready to transmit it over on the wire. And so while all this is going on, the receive machine has actually prepared a packet buffer in main memory and given it to the network card. So the network card now has free space in main memory. It can simply write the new packet into. Once that is complete, the receive NIC, in fact, has to update some metadata in main memory, again, mostly containing the packet length and maybe some valid bit. At that point, the NIC raises an interrupt to the processor, which notifies the processor that there is a new packet it needs to go fetch from main memory and process it. Now, to complete this picture, all the transmitting machine still needs to do is it needs to free up its transmit buffers that it has allocated in main memory. Now, as you can see, there's a lot of going back and forth over the PCIe. In fact, there are 8 total PCIe transitions in this path. And 6 of those are synchronous, meaning that the next one can't start until the previous one finishes. And on top of that, there are 4 accesses to main memory. So we're communicating to main memory. There is a few accesses to memory there. Now, imagine you're sending out a small packet, a 64-byte minimum size packet. And this is not very hard to imagine because in a typical RPC system, actually, over half of the packets tend to be very small. So you have lots of very small packets that you need to transmit. And so if you're using this interface to send out a very small packet, that just doesn't look like it's very low latency. And it's not. And so we had some quibbles with this and decided we wanted to do something better. And we came up with this. So as you can see here, we actually don't go back and forth over PCIe. We simply go once over it on the transmit machine and then once over it on the receive machine. And that's the best you can do. We also do not communicate through main memory. Now, main memory is pretty fast, so you might not think that's a big win. But if we're not communicating through main memory, we don't need any memory buffers. Which means we don't have to allocate those buffers, we don't have to manage them, we don't have to free them. So it ends up being a bit of a win. All right, I'm gonna tell you briefly how we actually achieve this. So first thing we decided was that we're going to communicate from the CPU to the NIC directly, and we're going to use cache lines. So all of our communication is going to be in cache lines. All of our descriptors and our completions are going to be cache line wide. And this is nice because the memory hierarchy in the CPU is already optimized for cache line communication. So for example, on the transmit side, we're going to map the NIC memory as write gathering, which means that now, because we have this cache line, we can embed small packets inside that cache line. And the CPU prepares this small packet in a buffer, in its write combining buffer, before it just ships the entire packet over to the NIC, over the PCIe. On the receive side, we map that memory as cacheable, which basically means we issue cache misses to the NIC to fetch a cache line of data. And then we embed the entire small packet inside that cache line that we return. Another thing we do is we do not use interrupts. In fact, we use polling, and we poll on the network card instead of polling on host memory location. I'll get into that in just a little bit. I just want to first complete the interface here and mention that while using this cache line communication for small packets works out fine, large packets tend to be on the order of 20 cache lines, and at that point it just becomes inefficient. So for large packets, we use the DMA engine on the NIC. We still use cache line wide descriptors. Now instead of the packet, we embed the packet headers in the cache line, and then just use the DMA to fetch the packet data from the main memory. All right, let's get back to polling and interrupts. So historically, interrupts have been a good way to do notifications. And the way interrupts work basically is while the network card is waiting for a new receive, the CPU can sleep or be busy doing some other work. And then once a new packet is received, the network card will write it to main memory and then interrupt the processor saying, hey, there's a new packet you need to go fetch from main memory and process. Now, as I said, this works fine, but as I'll show you in the next few slides, this can actually be pretty high latency. A typical low latency way of doing notifications is to use polling. And this is usually done by polling on the memory location in host memory. So while you're polling on a memory location in host memory, and you're doing this in a tight loop, the memory location actually gets cached, and the processor is actually spinning really fast on that memory location. And this ends up creating a lot of useless work because this polling loop is actually really fast. And then once the NIC actually has some useful work, and it does write to the memory location that you're polling on, that will actually invalidate your cache line in the cache, and you will now incur a cache miss just to get the data that you require to process the packet. Now we actually chose to instead of polling on a host memory location, we chose to poll on the NIC. So we were polling on the location that's mapped to the NIC, and we're actually issuing cache misses to do this with. This has the benefit of slowing down this tight polling loop and actually creating less useless work, and also avoiding communicating through host memory. One of the things we had to do was on the network card, we actually hold the read for a while in anticipation of a new packet coming in. So we actually hold it for around 20 microseconds, anticipating there might be a packet coming in. If the packet does show up, we immediately return to the CPU with the cache line that has the small packet. And that cache line ends up all the way in the L1 cache and is ready to be processed. All right, so we actually build this. We build this interface on an FPGA platform. We use the NetFPGA, which is a Xilinx Vertex 5 development platform. And of course, we went ahead and we implemented all the necessary drivers we implemented in the user space to evaluate our interface. And as a driving application for the evaluation, we used a very simple object store. So this is a very simple object store that supports only a get and a set operation. And the simplicity actually allowed us to focus the evaluation on the network interface itself. We put some effort in implementing both our user space driver and the Intel X520 user space driver in quite the same, in similar ways, and integrating them in similar ways so that we get more comparable results. And I'm going to show you now some of the latency numbers that we have. And all of those latency numbers are actually a round-trip latency numbers. So going from a client application all the way to the server application and back, round-trip numbers. So first, we ran our application on an Intel card, Intel X520 card using the interrupts, just for a baseline of what you might get in today's data center if you ran this. And we did the evaluation on very small objects, 4-byte objects, all the way to 1,400 byte objects, and we got results that were in the 20 microsecond range. Then we went ahead and we ran the same experiment on the same Intel card, but now we used polling, and we got about 2x improvement. Now, there are two things important here. One, as I mentioned, this was a round-trip measurement. So there are actually two interrupts that happen in the interrupt case, two receiving critical path interrupts. And the second reason why polling is so much better is there's actually quite a bit of operating system's code that gets executed when you raise an interrupt on an idle machine. You have to go through your interrupt handler, but then you have to call schedule. You have to schedule in the process, and then once the process is scheduled in, you can process the packet. So this was the Intel card, and then our interface actually achieves better. We get under 5 microseconds for small packets, and we also get some improvement, just under 10 microseconds on the large packets. And this is the interface that I described with all the features that we implemented. We also went ahead and did the bandwidth evaluation. We ran a bandwidth benchmark, and we were actually a little bit surprised that we beat the Intel card on the bandwidth benchmark. We didn't try to optimize for bandwidth. We optimized for latency, and this just goes to show that if you engineer for low latency, the bandwidth it will yield high throughput on its own, where the converse is not true at all. Optimizing for bandwidth often sacrifices latency quite a bit. All right, I want to switch gears a little bit now and talk about power management. The way power management manifests itself in our example is in the latency versus power trade-offs. So we did some experiments. We ran some experiments to evaluate latency and power on our system, and I'm actually going to show you the latency and power numbers for various processor power states, for various idle states. And this goes from C0 states, which are just active states, and you can run your processor in these active states at various frequencies, from something very low all the way to turbo mode. Another state, the C1 state, is the case where you clock gate the processor, and this state is something that the processor goes into when you call a halt instruction. And then finally, there are some deeper states, like the C3 state, where you start turning off some of the local caches. And then finally, the deepest of C states, like the C6 and C7, in which cases the entire processor cores are power gated and they're powered off and caches are flushed. So naturally, there's a power versus latency trade-off here, where some of these deeper idle states do save you power. You get lower power. But it takes a while for the processor to get out of those states and back into the active C0 states where you can actually process instructions. And so to measure this, we came up with an experiment where we used our NIC, basically our FPGA card, to generate packets, basically generate writes that go to the application that is polling on a particular memory location, and then simply signaling back to the FPGA to stop the measurement, stop the clock. And so this experiment measures the wake-up latency off our processor and has an overhead of the PCIe round trip. Now we can poll in these active states, but in the idle states we can't really do polling. You can't. Polling is an active processing state. If we're in one of the idle states, we use the monitor M-wait instruction, where we monitor the memory location where the FPGA is writing into, and then we're M-waiting, and the M-wait goes and places the processor in one of these deep idle states. And so when the FPGA generates a write, the processor will actually have to incur this wake-up latency trying to get out of that state and ready for processing. So on the right-hand side, the power measurements are simple. We simply measure the power of the idle CPU and memory in various power states. All right, so I'm going to show you some numbers finally. So for some of these deep power states, like C3 and C6, while you do save some power, the latency is just off the chart and through the roof. So you can see the numbers up there. The latency is actually in 30 to 40 microsecond range. And if you remember our motivation slide, our goal was to reach a 5 microsecond round trip. So these latency numbers are just a non-starter. We simply cannot use the deep power states if we want low latency. We get a little better if we use the C1 state, but we get a lot better if we just keep our processor in an active state. You can see that the latency in the active state is actually the lowest, and this is basically only the overhead of the PCIe round trip, because in an active state there is no wake-up latency. And on the right-hand side, you can see the power numbers, whereas you might expect they dramatically increase as you increase the frequency in the active state. I don't know if you can see, but the frequencies are from 1.6 gigahertz all the way to 3.6 gigahertz. Yes. So looking at this graph, if you were trying to find a good compromise between a power state for a low latency and reasonable power, you might go ahead and pick something like this. It's an active state, so you're still in an active state. You get low latency, but you want to keep your frequency lower so that you don't waste any power that you don't have to. Naturally, if you have a lot of work to do, you eventually want to raise the frequency and get into a better frequency range. All right, so in conclusion, we built a low latency interface that minimizes the number of PCIe round trips. We really focus on minimizing the PCIe round trips, especially for small packets. So we optimize for small packets because we believe over half of the packets in a typical RPC system are going to be small packets. We also did some work on investigating power and latency trade-offs. And the results we achieved were under 5 microseconds. We achieved around 4.7 microsecond application round trip for our interface. And then we went ahead and we tried to guess what would happen if we, instead of having an FPGA card that we had, what would happen if we had a better card, a state-of-the-art components, or if we had an ASIC implementation. And we kind of guesstimated that we can get even around 2x better. So we could get around 2.3, 2.4 microseconds. All right, that's all I have. I'll happily take questions.
From Lab, I have a question. For your small packet, it goes through directly operator the NIC memory, and for big packet, it still go back to the RAM memory. So does that make your NIC design complicated or your driver design more complicated?
That's a good question. Does it make it complicated? Yes and no. So now you have two interfaces instead of one interface, right? So if your application wants to send a small packet, it kind of needs to use a different call, a different library call to send out this small packet. So it is complicated in that sense. But a lot of the implementation and a lot of the hardware implementation actually is just a small extension where we use the cache line wide descriptors and completion entries in both the small and large packet case. And so for small packet case, we just embed the entire packet. For large packet case, as I mentioned, we embed the first 48 bytes. So basically embed most of the headers, or all of the headers of a large packet. So in terms of doing hardware and processing, it's actually quite similar. We still have chunk of the packet in the descriptor. Now it's just a matter of whether we do have to go and fetch more data out of main memory. So yes, it's a little bit, it adds a little bit of complexity. It's actually not that bad. And then in terms of driver implementation, like I mentioned, for small packets, we don't communicate through main memory at all, which actually simplifies some of the driver in the sense that you don't have to allocate new buffers. You don't have to allocate transmit buffers at all, and you don't have to free them later because you're not going through main memory. You're basically creating this packet in a write combining buffer in the CPU and just shipping it over to the NIC directly. I'm not sure if that answers your question or it makes you more comfortable that this is not super complicated.
Oh, thank you.
Hi, I'm Eriksson from Norsk Tipping, Norway. Just for fun, did you ever try to do these simulations with jumbo frames?
No, we didn't do jumbo frames. We stuck to a 1500 maximum size packet. There's no reason to think that anything different would happen. I don't know if you have anything in particular in mind. Why would jumbo frames make life different?
No, I don't. I just wondered because we're using jumbo frames in some areas of our network, and we always want to have lower latency. So. Right.
So, I mean, we've investigated how far you can push the small packet interface, kind of. So we investigated, well, if we go one cache line size or even a couple of cache line sizes, you can actually communicate this directly. You can just have the CPU write out to the NIC. But even at 1,500 bytes, that's not really feasible anymore because now you're just wasting too much CPU throughput. So we went back to a DMA interface. So for jumbo frames, it would just be a bigger DMA read, basically.
Okay, thank you.
Thanks.
Hey, great work. Really like what you just presented. What I'm wondering is, I guess with FPGAs, you always have this problem of really long development cycle. So I was wondering how much of real NIC functionality is actually there, and if anything is missing, which is kind of would stop you from using it, let's say, with other experiments. So basically my question is this something which is a minimal design that works with this get-put operations? And if yes, then adding the additional functionality to have it a little bit more general would change the latency at all, or not really?
Right. So the NIC is completely there. You can send out any Ethernet packets. There's complete NIC functionality. One of the reasons we build this on top of a net FPGA platform is because it's meant for networking research. So we actually got the 10 gigabit MAC and got the PHYs and got the PCIe, the Xilinx PCIe core from Xilinx. So we had some of the infrastructure there. So there's the NIC is it's a complete NIC. You can, if you wanted to, you can web browse using this NIC. The reason we use the minimum kind of object store application is we kind of looked at what would it take if we wanted to take, say, memcached and run memcached on this. Well, there's a lot of things happening in memcached, and it seems like the variability of if you start tweaking memcached and you start changing things, you're gonna have these several microsecond gains or losses just based on what's going on in software. And that will kind of mask our gains in the interface. So we just stuck with the simplest thing we could to show that our network interface works well.
Hey, JPVMware. I really like this work. I had a question about the cache mechanism. So in a regular world, what happens is you have this transmit ring, and you have this concept of ownership between the NIC and, basically. So you offloaded all of that to CPU cache line. And I'm wondering, what are the mechanisms that your CPU is giving you to manipulate these CPU, these cache lines and transfer ownership? Like the NIC will say, okay, this one I took care of it, and make sure these caches are not invalidated by other, process running. I mean, I'm not too clear about the cache mechanism on the CPU.
Okay, not entirely sure what you're referring to.
Okay.
What do you mean?
So I think
mechanism?
what I'm saying is your CPU is going to say, okay, I have this packet which is ready, so I'm going to load it in one of the CPU cache line. I mean, if I understand properly. Now, the NIC is going to send it, obviously, at some point, and it needs to let the CPU know, okay, this cache line is taken care of.
Okay.
And, this kind of thing.
I think I get what you're asking. So what we did is actually we mapped the whole range of memory addresses basically to the NIC. So now there's memory that lives on the NIC.
Sure.
Say there's 128 cache lines on the NIC, and this is all memory mapped. And so the CPU will now simply do writes to those addresses. The memory doesn't live in host memory, it lives on the NIC.
Sure.
And it's mapped as write gathering. So it'll go over PCIe to the NIC. And so then the NIC will eventually, depending on how big these buffers are or how many credits you have, eventually the NIC does have to go back to the CPU and tell it, hey, I've processed 10 or 32 or 50 of your transmits. They're done, so you can reuse those. So there's credit-based flow control in there that controls how many of these cache lines have been processed and it can be reused.
Okay.
I'm not sure if that answers your question.
Hi. Kostas, University of Rochester. This is not something specific about your work, but it is in general something that I observe when someone works with accelerators and you're working with a network packet processing accelerator. These machines tend to go to great lengths to avoid the overhead of the operating system, right? And as soon as we do that, we don't have a mechanism to, for example, in the particular case that you're working with, to throttle between processes that could have different priorities in the way that they should be accessing the network. Yeah, I would like to hear your thoughts on whether and how we could possibly re-engage the operating system in the decision-making and in scheduling for networking devices like the ones you're working with.
So if I'm getting this correctly, you're wondering about sort of multiplexing between different apps and how you can have the OS do that. Yeah, it seems like that's just the state of everything these days, where if you want low latency, you just go ahead and you bypass the operating system and just take the ownership of the NIC, and that's kind of what we did. In terms of how we can move that ownership back to the OS, well, frankly, if you want the lowest latency, that's going to be a little tricky. One of the things that you could do is you could have the OS sort of manage. So most of the NICs these days have just multiple queues. You can have almost any number of queues you want. One of the things you could do this is you could have the OS sort of dedicate some of the queues to a particular application. So if an application wants really low latency, it asks the OS for 3, 4, 5 queues, and then the OS manages that and then just hands off the queues to the application so that the application can manage it itself. And that would be a good way, for example, in my opinion, for an OS to kind of provide same functionality for multiple applications. Sure.